Hello everyone. The traveling salesman problem is one of the very well-known problems in computer science. The problem goes like this. A salesman has to visit n cities such that he visits each city exactly once and the distance that he needs to travel is minimized. The problem can be formulated as a graph theory problem where we need to find a Hamiltonian cycle of least distance. This problem is hard because it is NP-complete. That is, the complexity of the problem increases exponentially with the number of nodes in the graph. However, we can still attempt to solve such a problem by methods that guarantee an optimal solution in most cases and a close to optimal solution in some rare cases. Such a method is usually good enough for practical applications. One such method is called ant colony optimization, which is influenced by optimal pathfinding techniques used by real ants to find food. To explain how ant colonies can find optimal paths to a food source, let's imagine an ant colony located at point A and a food source at point B. And let's say there are these two paths from A to B, a shorter one through C and another longer one through D. Now imagine two ants, ant 1 and ant 2, that move along paths ACB and ADB respectively. Once both these ants reach the food source at B, they return back to the colony and along the way drop what we call pheromones. Pheromones are these chemical substances that help other ants navigate their way to the food source. The interesting thing about pheromones is that they evaporate at a constant rate with time. So as you can imagine, by the time both our ants reach back to the colony, the concentration of pheromones on the shorter path would be higher than that on the longer one, since it takes longer for A2 to return back. Consequently, more and more ants would venture out to get food, and the chances that any new ant would take either of these two paths would directly depend upon the pheromone concentration. So as time progresses, the density of pheromones on ACB would get higher and higher, and eventually all the ants would gravitate towards the shorter path. And this is how essentially ants find optimal paths towards a food source. Or generally, let's say we are at node I on a graph and we need to choose one out of n neighboring nodes to hop to. The probability that we choose neighbor j is given by Pij equals Rij alpha times Sij beta divided by the sum over all neighbors of I, and basically the same quantity Riz alpha times Sic beta. Here R is the pheromone concentration on edge Ij, and S is the static probability weight of choosing edge Ij. The static probability is a greedy choice which encourages traversing shorter edges. So we can imagine this to be a quantity given by K of Lij, where K is a constant and Lij is the length of edge Ij. And alpha and beta are parameters by which we can vary the influence of pheromone concentration and static weights. In optimization, we always need to strike a balance between exploitation and exploration. Exploitation indicates accumulated knowledge and hence searching further close to known solutions. Exploration, on the other hand, searches the unknown space. Too much exploitation can lead to suboptimal results, and too much exploration can lead to slower convergence or no convergence at all. In this case, pheromone concentration is accumulated knowledge, and hence alpha can be called the exploitation parameter. And static weights remain the same, and these probabilities are fairly equally distributed. And so following them is tantamount to random search, and hence beta can be called the exploration parameter. In any optimization technique, finding a balance between alpha and beta is extremely important. Initially, all edges have constant pheromone counts, and hence the probabilities are determined using the static weights. After BNs have traversed the graph, the pheromone concentrations are updated according to this equation. Here, delta Rxy is the pheromone concentration added to edge xy. E is an evaporation rate. So we take the previous concentration and multiply it by 1 minus E. And then we sum up the pheromone counts dropped by all the BNs on that edge. And that is given by Q over Lk in case the kth ant traverses the edge xy and 0 otherwise. Lk here being the difference between the length traversed by the kth ant and the length of the best path seen so far. So what you saw previously was this Godot application. Let me walk you through the most important bits of code. So the script is really simple. I'll just go through the ant colony optimization part. So basically this is the function which runs ACO batch. Initially we run the evaporation. The evaporation is quite small here, it's 0.001. And then we modify the weights. We get a random path for every ant. And then we calculate the difference between the best length. And then in order to avoid division by 0, we add a small number here. And then our score of the path is given by small constant divided by the difference. So this ensures that paths which are closer to the best path are weighted much higher. And then for all the nodes, we get the indices of the nodes and then increment the weights from the index 1 to 2 as well as index 2 to 1, because the score of a path should be the same when traversed forward as well as backward. The transition probability, as I explained before, is basically the combination of exploitation and exploration. Exploitation is the weights, which are basically the pheromone concentrations to the power of alpha, times 1 over the lengths between nodes 1 and 2 to the power of beta. And how we sample a random path is, again, simple. We start off at any random node. We check for all the next neighbors which have not already been traversed. We get the transition probability to that neighbor and append it to a possible list of transitions. Then we choose a random number, and depending on the number, we choose a neighbor to transition to. And then once all the neighbors are traversed, we get the path, we calculate the distance traversed through that path and return the path and the distance. And that's basically it. The rest of the code just adds the nodes, adds the weights, calls generates, handles input, and so on. And that was it. You can find the code to this project on GitHub. And as always, thanks for watching.